We are on a collision course with our neighboring large galaxy, Andromeda, a system of several 100 billion stars. This collision will lead to a mutual descent, altering both galaxies in significant ways. The Andromeda Galaxy, historically vital in showing that the universe did not revolve around us, has been the focus of astronomical study for over a century. It was Andromeda that proved the Milky Way was not the only galaxy, shifting our understanding of the cosmos. While much has been learned from Earth, advancements like the James Webb Space Telescope have provided new, shocking insights about Andromeda that we didn't foresee for an entire century. Just over 100 years ago, the Milky Way was perceived as a faint band of light across the night sky due to limited technology that prevented the discernment of individual stars. Various beliefs about the Milky Way centered it in creation. This changed in the early 17th century when Galileo Galilei used his telescope to observe that the Milky Way was not just a band of light, but a vast collection of stars, planets, and celestial objects. Galileo's work debunked the notion that the Milky Way was the center of the universe, revealing it as a sprawling expanse of stars. In 1750, English astronomer Thomas Wright hypothesized that the Milky Way was a flat layer of stars, including our solar system, a theory limited by the technology of his time. By the early 1900s, significant advancements were made in astronomy. In the 1920s, Edwin Hubble used the Hooker telescope at Mount Wilson Observatory to demonstrate that distant nebulae, including the Andromeda Galaxy, were separate galaxies with billions of stars, fundamentally transforming our understanding of the universe. The Andromeda Galaxy, also known as M31, has been observed since at least the 10th century, when Persian astronomer Abd al-Rahman al-Sufi described it as a small cloud. Al-Sufi's keen eyesight allowed him to identify Andromeda without telescopic instruments, a feat possible because Andromeda is one of the few galaxies visible from Earth's surface without special instruments. It wasn't until 1612 that Simon Marius provided a telescopic description, laying the groundwork for future astronomers. In 1764, Charles Messier catalogued Andromeda as M31, furthering its recognition. A major leap in understanding Andromeda occurred in 1864 when English astronomer William Huggins studied its spectrum, finding it different from typical gaseous nebulae, which was a pivotal observation. Andromeda is massive, with a mass estimated to be between 1 and 2 trillion times that of our Sun, and is thought to be about 10 billion years old, suggesting a complex history of formation through the merging of smaller proto-galaxies. Previously, astronomers thought Andromeda was significantly more massive than the Milky Way. Recent research has revised these estimates, showing that the masses of both galaxies are much closer than previously thought. The Andromeda Galaxy's physical dimensions are larger than the Milky Way's, with a diameter of about 220,000 light-years compared to the Milky Way's 100,000 to 175,000 light-years, highlighting its vastness. One of Andromeda's fascinating features is its active galactic nucleus, powered by a supermassive black hole with a mass between 110 to 230 million times that of our Sun. Observations using advanced telescopes, like the Hubble Space Telescope, show 2 points of concentration in the Andromeda Galaxy, with the brighter one slightly off the true galactic center, indicating intense gravitational interactions and the presence of a supermassive black hole. Andromeda also has an abundance of globular clusters, estimated at around 460, each containing hundreds of thousands to millions of stars. This abundance indicates Andromeda's history of galactic cannibalism, where smaller galaxies were absorbed into Andromeda, adding to its stellar population and diversity. Recent observations suggest that Andromeda may be transitioning from a typical spiral galaxy to a ring galaxy, a relatively rare type characterized by circular ring-like structures of bright young stars. Ring galaxies can form through galactic collisions, or when a smaller galaxy passes through the center of a larger one, making them unique among galactic structures. The impending collision between the Milky Way and the Andromeda Galaxy is a cosmic event predicted to start approximately 4 billion years from now, and will unfold over the subsequent 2 billion years. This grand encounter will culminate in the formation of a new supergalaxy, which has been nicknamed Milkomeda by astronomers and enthusiasts. The merging process will be characterized by significant gravitational interactions and tidal forces profoundly affecting both galaxies. As the Milky Way and Andromeda approach each other, their immense gravitational forces will begin to distort each other's shapes. This gravitational interplay will pull stars, gas, and dust from each galaxy, creating elongated tidal tails and triggering a series of complex gravitational interactions. The overlap and mingling of the two galaxies will not be a smooth process. Instead, it will be marked by chaotic and dynamic changes as their structures are gradually dismantled and reformed. One of the most dramatic consequences of this collision will be the formation of new star clusters. As the galaxies merge, the gas clouds within them will collide and compress, leading to bursts of star formation. These stellar nurseries will be regions where intense gravitational forces compress the gas to the point of collapse, forming new stars. These newly formed stars will often be grouped into clusters, enriching the new supergalaxy with fresh stellar populations. At the same time, the gravitational turmoil will cause changes in the orbits of existing stars. Stars that were previously in stable orbits around the center of the Milky Way or Andromeda will be thrown into new, more elliptical paths, or potentially flung out of the merging system entirely. Some stars may find themselves ejected into intergalactic space, becoming rogue stars no longer bound to any galaxy. This redistribution of stellar material will contribute to the formation of new cosmic structures and may result in an intricate web of star streams and clusters that blend the remnants of both galaxies. In addition to forming new stars and clusters, the merging process will also create massive, complex structures within the new galaxy. The gas, dust, and stellar debris from both galaxies will mix and settle into new configurations, forming vast regions of star formation, spiral arms, and potentially new galactic features that are a hybrid of both the Milky Way's and Andromeda's original forms. These structures will evolve over time, influenced by the new dynamics of the merged galaxy. The supermassive black holes at the centers of the Milky Way and Andromeda will also play a crucial role in the merger. As the galaxies coalesce, their central black holes will eventually merge, creating a single, even larger supermassive black hole at the core of Milkomeda. This merged black hole will be a powerful source of energy and will have a significant impact on the surrounding stellar environment, contributing to the new galaxy's dynamic and evolving structure. Ultimately, the merger between the Milky Way and Andromeda will result in a completely transformed cosmic landscape. The new supergalaxy, Milkomeda, will be a colossal entity composed of the blended material from both progenitor galaxies. It will feature a rich tapestry of new star clusters, altered stellar orbits, and restructured galactic features. This process of cosmic evolution driven by the collision and merger will shape the future of the local group of galaxies and provide a fascinating glimpse into the long-term dynamics of galactic interactions. The merger will result in profound changes to our night sky and the environment on Earth, potentially affecting habitats, biodiversity, and climate. However, this process will occur long after humanity is gone, as our sun will evolve into a red giant and render our solar system uninhabitable in about 5 billion years. The merger of Andromeda and the Milky Way raises questions about the fate of our solar system and the formation of new galactic structures. The cosmic interactions will shape a new galactic environment, possibly with habitable zones for potential life forms, although vastly different from what we know today. The Milkomeda Galaxy will be a testament to the dynamic and ever-changing nature of the cosmos. The collision between the Milky Way and Andromeda, predicted to occur in about 4 billion years, will be a spectacle of cosmic proportions. It marks the culmination of a gravitational dance that began billions of years ago, when these two colossal galaxies first started their inevitable approach towards each other in the vast expanse of space. As the merger progresses, one of the key phenomena astronomers anticipate is the transformation of both galaxies' spiral structures. Currently, the Milky Way and Andromeda are spiral galaxies characterized by their prominent arms extending outward from a central bulge. These spirals are defined by the rotation of stars and gas around a central core, creating distinct patterns observable from Earth. However, as the galaxies draw nearer and their gravitational influences intertwine, these spiral structures will undergo significant changes. The mutual gravitational attraction between the Milky Way and Andromeda will distort their shapes, pulling and stretching their spiral arms into elongated tidal features. These tidal tails will be composed of stars, gas, and dust that have been pulled away from their original galactic disks, creating a chaotic yet mesmerizing display across the cosmic landscape. The collision will also trigger intense bursts of star formation within the newly forming supergalaxy. The interaction of gas clouds from both galaxies will compress and heat up, leading to the formation of massive, luminous star clusters. These clusters will become the nurseries for young stars, whose energetic radiation will illuminate the surrounding cosmic dust and gas, giving birth to new stellar populations. The merging process will not only affect the appearance of the galaxies, but also their internal dynamics. The gravitational interactions between stars and gas clouds will cause a reshuffling of their orbits and velocities. Some stars will be flung into more eccentric orbits, while others may be expelled entirely from the merging system, becoming free-floating rogue stars in the intergalactic void. Meanwhile, the supermassive black holes at the centers of the Milky Way and Andromeda will play a pivotal role in shaping the future of the merged galaxy. These behemoths, each millions of times more massive than our Sun, will eventually spiral toward each other under the influence of gravitational waves emitted as they orbit closer and closer. The final stages of the black hole merger will be cataclysmic, releasing enormous amounts of energy into space in the form of gravitational waves and radiation. This merger event will create a single, even more massive supermassive black hole at the heart of the newly formed galaxy, surrounded by a swirling accretion disk of gas and dust. The presence of such a powerful central engine will have profound implications for the evolution of the supergalaxy.